Okay, so we're doing the oxidation of alcohols, and the syllabus makes note of, well, isn't that combustion? And so just be aware that combustion is 100% oxidation, and what we're doing is partially oxidating, not going the full whole hog and doing the complete oxidation, which is this. Okay, and while we're doing that, I may as well just revisit. These are some legacy slides that they've sort of taken out, and the big one they've taken out is having to know the actual names of the oxidants and their color changes, and we'll leave that in there just to let you know why. And so while we're at it, I'll just revisit this fuel one again. So the energy released from all these alcohol fuels increases because it's per mole and the molecules are just bigger. And so that's why that one there seems a bit silly to state. All right, more carbons, more energy released. This one is the one I wanted to go into a little bit more. So that when you increase, so comparing to methane, when you increase the oxygens in a molecule and do this instead, it burns cleaner because then instead of having carbons, you're getting water coming off. And so, but the problem is it decreases the amount of energy that's released. And so you have to do a more in-depth analysis to work out what it is. And the reality is it's because you've got, methane's got more carbons, and the more carbons to oxygen ratio. And it's the carbon bond that's carbon oxygen bond that's really stable and releases the most energy. And so that's why having the least number of oxygens makes it more energy dense, but then it also releases more carbon dioxide because that's where you're getting the energy from. And so if I just revisit this bond enthalpy, so working out the enthalpy using bond enthalpies, so there's all the Lewis dot structures, and then you work out how many bonds there are, and then you put in the numbers in there. Basically, there's the big number. These are all like 400s. And so if you break the oxygen and reform it, so break that and reform that, so you get two of those instead. They're all about 400. It's the more of these you can form the 800s. And so that is the number that sort of tips it here in the balance of releasing. So you can see the methane, because there's 2 moles there, so I had to double this number, is higher because there's more of those bonds getting formed. They're very strong, so they're releasing a lot more energy. So that's the reason. All right, let's get into what we're here for. Oxidation of alcohols. Okay, because of steric hindrance, you've got to remember that there are hydrogens over here. There's CH3s. And so there's all this steric hindrance, so access to this is limited. You can't get in there. Okay, and so they're generally not reactive. They will react, it says not easily. Okay, and when we say all this sort of stuff too, this in lead purification, because we're not just going to get 100% perfect clean reactions without anything else going on. Okay, so the way I learned this one is I just try and slowly make it more and more oxidized. Obviously, I'm not going to reduce this to CO2. It's not going to happen. It's in liquid to start with. You have to get rid of all the water and then activation energy. Although you could find a way to do it. But anyway, I know what my functional groups are, and I just try and remove a hydrogen or add an oxygen in order to make it more oxidized than what it was. And if you have a careful look here, this one here, we can't really add an oxygen anywhere because I'm not allowed to break any of these bonds, the carbon-carbon bonds. And if I remove one oxygen here and put two oxygen, I can put a double bond and get a ketone. All right. This one here, I can't get a ketone because if I put a double bond in here and did the same thing, which is what happens, I get an aldehyde. So I'm sort of doing the same thing, but because of the way functional groups are named, it's still giving me a carbonyl group, but one's a carbonyl group for an aldehyde, one's a carbonyl group for a ketone. And then I run out of hydrogens I can remove or oxygens I can add because it's already got 4 bonds. So adding the oxygen is difficult. I technically didn't add an oxygen. I'm just taking hydrogens right now. And I've still got 1 bond I can break. I can't touch these guys. And so I could still add an oxygen to that and turn that into a carboxylic acid. And so that's mentally how I think about it. Okay, so I can see that there's either a progression of decreasing hydrogen or a progression of increasing oxygen, and they're the things that I can do as a progression of further oxidation, and so that's how I do it. Okay, I don't try and memorize it. Okay. And so this is practically speaking in the lab, this is what you're going to do. You're either going to grab potassium dichromate that goes from yellow to green with those oxidation number changes, or you're going to get potassium permanganate, which goes from pink to yellow. Is that reduces brown to purple or clear? God knows. All right, so I think they're the textbook answers. That's saying the textbooks disagree with each other. Okay, so manganese, some textbooks go, I think they go pink to brown, and some go pink to clear. The problem is it's going from one to the... I think this is why they got rid of it. So you don't need to know this anymore. They got rid of it and used to have potassium permanganate or potassium dichromate, and you had to say which color it was. And the textbooks all disagreed with each other. And the reality is it changes many, many different colors because of this. So you've got stable... These are probably the most common ones, purple, but does that really purple or is that pink? So the symbol we're going to go for oxidant, which is the one that gets reduced, is this plus O in the brackets. And we'll go for the plus H for reductant in the reverse, which is coming in the next video. You're going to have to learn this. You don't have to learn the mechanisms for this, but you're going to have to know that primary alcohols go to aldehydes and carboxylic acids, secondary alcohols go to ketones. All right. You're also going to have to understand why we use distillation and why we use reflux. And you can see that if you can remember, this one's got hydrogen bonding. This one's only got dipole. They're about the same size. That one's got the dimers. Okay, so this one has way higher than this, even though they're both almost the same thing with hydrogen bonding. And so that's why that one's way higher in melting boiling point. And this one's only 20 because it's just got dipole. All right. So the problem is once you start if you want aldehyde, that's fine. You just distill it and it goes to a 20 degree boiling point, so it just comes off very, very easily, and you condense it and collect it down here. That's all well and good. But if you want the carboxylic acid, you've got to let it keep reacting. You've got to let it fall back down and keep reacting. And once it gets to a carboxylic acid, you don't have to worry about it, because the first thing that's going to boil off is alcohol, not the carboxylic acid. So then we have to, if we want aldehydes, we use this setup. If we want it to keep going, we use a reflux. Keep the lid off so it doesn't shoot up and cause trouble. All right, so the pressure doesn't build. So hopefully, as you're doing this, there's no gases escaping, and by the time they get close to the top here, they're condensing, and the aldehyde keeps falling down, so they can get further reacted to carboxylic acid. Okay, so you have to know the two systems and why and how they work.